So discrete random variable in S1, it could be hard because, well, okay, let's say the variation of difficulty level can be wide, because when it's easy, it's very easy. When it's hard, it's just a head scratcher. Like, because the problem usually involves real world application of statistics. It will use this thing to model a situation. It can be as simple as rolling a dice, and to, an example where you want to calculate the profit, expected profit from some sales. And it can get complicated depending on the question. So if they want to make it so complicated, they can do that very easily, right? Because there are a variety of problems that this can apply. So that's DRV. The keywords here to know is that it's discrete. That means whatever the situation you want to use this to model, the value of something will be discrete. So let's say you want to model the probability distribution of like the number of items you sell in a week. Let's say you sell ice creams. So in a day, you might want to know how many ice creams you sell. All right. So the number of ice cream will be a discrete value. Cannot be 1.5, right? You just say 10 ice creams or 12 ice creams or whatever in a day. So discrete is important. So cannot be just a discrete value in the event, e.g. number of ice creams sold and so on. Now, random means that the probability of each of the events in the distribution can be any value. But random in this case is like a big category, if you like. So you can also say that a discrete uniform distribution is a discrete random variable. So the word random here include everything from rolling a dice to any random situation. Let's say you want to find the probability distribution of how many days you wake up late in a week. Let's say you go 2 months in a row, so about 8 weeks or 9 weeks. And then in the 9 weeks, you want to sample, like you want to experiment how many days in the week you wake up late, later than 7 p.m., sorry, a.m. maybe. So the numbers might be quite random there. So there you go. That's the random distribution. So the probability of you waking up late in a week might be different week by week. So this is unequal probability in the event. Okay. Variable in this case refers to the X usually. So is the X. It's just the thing that can change. For example, if you go back to the case of selling an ice cream in a day, selling ice creams in a day, so X would be the number of ice creams. Going back to the case where how many days you wake up late in a week, X would be the number of days you wake up late in the week. It can be anything, all right? But it represents the quantity of something. So quantity of something in the event. All right. So when we put them together, it is just a probability distribution of some event of interest where you want to know about the probability of each of the variables. So normally, when we put this together, we refer to it as probability distribution. So whenever you see this term, it usually is about a table of cases where typically you have 2 rows and number of columns depending on how many X values you have. Okay. The first header, the row headers would be a little X here. And the second row would be probability of the variable big X equals the small x. Now let's make it simple first. I'm going to make this just for the case of throwing a dice, and maybe it would be the probability of getting each number out of the dice. Okay, let's construct the table together then. So if you roll a dice and you say that variable x, so let's say variable x represents, the question will tell you like this. It's going to tell you what variable x means. So in our case, variable x represents the number showing on the top face of a thrown dice. So what are the options that X can take? If you throw a dice, what are the numbers? Yeah, so this is simple. So it's just the options. All the options possible, you write them down. And probability of variable X equal each of the number in the top, the bottom row, you just fill in the probability value. If it's a fair dice, what do you get? So 1/6 each. And fractions are fine in this case. We can do exact values. The rule of thumb here is that whatever table you come up with, it doesn't have to be equal, right? This is probably more like a discrete uniform variable distribution. The rule of thumb is that whenever you see this kind of table, you must know that if you sum up all the probabilities like that, that's just the notation. Don't be intrigued by just the notation. Just basically sum up all the values, you would get 1. Now, there is a new term. This is basically adding up probability. So we are familiar with this because you did the Venn diagram before and you did that all the time. You're adding up the areas to get 1. But there's something new in this topic. There is something called expected value. And this is the very highlight in the real world application of S1. The casinos and gamblers, they use this concept of statistics to get smart, basically. So whatever game they play, maybe the pro would like to calculate the expected value. Also, it also works in investment. If you say invest in stocks or crypto, whatever, calculating expected values might be wise. Now, what is it? It's more like a mean. So we write it like EX, like this, E big X, expected value. It is equal to, just like finding the mean in a frequency table. So it is equal to the sum of all the subtotals, where each is just the small x times the probability of that small x. So basically, in this case, you would do 1 times that, plus 2 times that, plus 3 times that, plus 4 times that, and add them up. This would be 1 times 1/6 plus 2 times 1/6 until the last case, which is 6 times 1/6. And that would give you about 3.5, I guess. Just a midpoint there, if you work out. It's almost done now. There is another one concept, which is variance. You can also calculate variance from the probability distribution. Okay, so variance, it comes again. We use the notation var x, but it is the same concept again. What is variance again? Like if you put it to common language, variance is, if you remember, mean of square minus square of mean. Yeah, it's the measure of average spreadness of the data. That's right. So it's mean of square minus square of mean. So mean of square is expected value of x squared. Again, I told you expected value of something is kind of like the mean of that thing. So mean of square is therefore expected value of the variable squared. EX squared. What about the square of mean in this case? Exactly. Square of the expected value. Exactly. Now let's have a brief about the concept of cumulative distribution. Okay, so a cumulative distribution is just adding something from the current probability distribution. So if you want cumulative distribution, the first row will be the same, but then what is cumulative? So I'm gonna copy this table first. So for the same event, the cumulative distribution is just basically adding up probabilities. Accumulate probability. So this would be 1/6 first, because you would bring 1/6 down here. There's nothing accumulated before 1/6. So the first one is 1/6. But then what we write here is this is fx equals x. So you accumulate the probability from the previous values of x. That means when you want to find this value, you need to add what has been accumulated to the new one, and then you got this one. So you have 2/6 there. So it's like adding that to that, you get this. Well, easily, this will be 3/6, 4/6, 5/6, and then 1. So you do always get 1 at the end, because that's where you add up all the probabilities. That means f of x equals some maximum value would be equal to 1, because you have accumulated from the very beginning to the last values. And that's kind of it. That's just the overall concept you need to know.